So we're going to go through Pearson correlation with regression from chapter 13. And we'll go through all the steps as far as what it's used for. So correlation research is probably some of the most common research used in social behavioral sciences. I'm sure you've heard of some of these, like violent television and violent video games. We have seen the violent media is related to childhood aggression. It's a relationship. An increased risk of heart disease is related to type A personality. If you recall from Psych 101, type A personality is that those people who are highly critical of others as well as themselves, very kind of perfectionistic and rigid in their thinking. We can see that there's a relationship between IQ and GPA. We can also see that stress is related to poor health. We see that our immune system is affected by stress. And we also know that exercise is beneficial when it's related to depression. So we could see decreased amounts of depression with people who exercise frequently. So this is all common correlational research that you've probably heard over the years. These are the types of things that are just looking at just relationships between variables. So that's the key to correlation research, is that we're looking at just merely a relationship between two variables, and the variables are measured on a continuous measurement scale. So either interval or ratio data. So for each person, there's two measurements from two different variables, not at two different points in times, but we're just looking to see, is there a relationship between those variables? So there's some characteristics of the correlation research that is important to understand. So the characteristics in particular that is important with Pearson correlation research is the use of being able to describe the strength of that relationship as well as the direction of that relationship. So when we're talking about strength of the relationship, we're talking about how much is one variable related to another variable. So if you'll notice, this says -1, right? So basically it's a perfect negative relationship. Every data point is on a straight line that shows as one's going up, the other goes down in perfect unison. So as you can see from this scatter plot, the data is just spread everywhere. There's no real pattern to it. So the relationship is weak or non-existent, basically. So that tells us the strength. Then we're looking at the direction of a relationship. So in the past, if you saw a negative sign, you were talking about, oh, the difference decreased, or the mean difference decreased. Or if you saw a positive sign, it was the mean difference increased. There was an increase. That's not how this is now. Now a positive sign describes that the variables move in an increasing direction. So as X goes up, Y goes up. So they're both moving up at the same time. And a negative correlation, if you see a negative sign, it means as X increases, Y decreases. So if you look at these relationships, this one here, the positive correlation, is temperature and amount of beer sold. So as maybe temperature goes up, beer sales go up. It's probable, actually. In this case, it's temperature and coffee sold, and this is specific to hot coffee. So as you can see, as the temperature gets up into the 80 degrees, hot coffee sales drop drastically. So you can see it's a negative relationship. As temperature rises, hot coffee sales decrease. So it's all about the strength and direction of a relationship. So to describe this, I'll move this out of the way a little bit. To describe this, the Pearson correlation uses what's called the correlation coefficient, which is R. R is the correlation coefficient. And so that measures that strength and direction of the relationship between two variables on a straight line, so a linear relationship. So as you notice in the previous, here we have a straight line, and the pattern of these numbers is around that straight line. They're not like all over the place. They're kind of going in a specific straight unison line. And it is what it talks about with strength. So for every change in Y, there's a specific change, or for every change in X, there's a specific change in Y. And the change, as it gets closer to that line, becomes stronger. And so with the Pearson R correlation coefficient, a perfect relationship is noted as +1 or -1. You can't have anything stronger than that. So that is a perfect relationship. A positive is a perfect positive relationship. A -1 is a perfect negative relationship. And then 0 means there is no relationship between the two variables. And there's any number in between. So a note to yourself, if you calculate your Pearson R, your correlation coefficient, and you get something that is like 1.12, you know you've done something wrong, because you can't have larger than 1. Because in actuality, a Pearson R is a probability. It's a proportion. And so your probability can't be more than 1. 1 is 100% probability, right? So it's based on proportion, so you can't have anything larger than 1. But the difference with Pearson is that you can have a negative, because it's not a true probability. It's the negative sign means that there's an inverse relationship. Just remember, like, it is relative to probability in regards to the fact that you can't have anything larger than 1. And so positive or -1, either one of those. Because the sign just tells us which direction. So when we are calculating the Pearson correlation coefficient, we're looking at the covariability of X and Y. So that covariability, or sums of squares of X and Y. And then we're also looking at the variability of X separately and Y separately in the denominator. So ultimately, this is our equation for Pearson R, which is known as the correlation coefficient for Pearson. So that equation is one that you're going to get used to over the next week or so. It's a lot of repetition with sums of squares, just using sums of squares in different ways now. So here's kind of what we're looking at. So this is different for you, the sums of square of the product X and Y. So ultimately, the sums of square X, Y is that basically the sum of X times Y. So for every X score, it has a corresponding Y score. You multiply them to. And then you're gonna take the sum of all your X scores and multiply them times the sum of all your Y scores, and then divide that by your sample size. So how many pairs do you have, basically? And then now you have the sums of squares X and sums of squares Y, which is sums of squares you've already learned. It's just you have it for Y and you have it for X now. So for every X score, you square each X score, add them up. Then you take your total sum of X, add it up, plug it in here, divide by how many are in that sample size. Same with Y. For every Y score, you square individually, add them up, and then you add up your sum of Y, plug it in there, square that total, and divide by N. So it's a lot of repetition is what it is. that sums of square xy is literally just another form of the sums of square equation. It's just a different way of calculating sums of square. It's basically the sums of square of the product. So x times y is the product. So when we're interpreting correlation research, it's really important for you to understand that correlation research does not demonstrate cause. So you can't say one thing causes another. I can't say that watching violent television causes people to be violent. I can only say there's a relationship. I can't say one causes the other. So we need to be really careful when we're talking about correlation research that we're never using the words cause or that one is the result of another. It's they're related to each other. Either there's a positive relationship or a negative relationship. And we also need to be able to be real careful about looking at our data. And we typically use scatter plots with correlation research. So we want to always look at our scatter plots and see, like when we're interpreting our correlation research, are we getting the right picture? So if you notice this top scatter plot here, if let's say this line was drawn right here and I gathered data and the only data I got was X scores that were this high out here. Well, if that was the case, there would be no relationship. Our data would show no relationship. So that would be, for example, if I decided to look at IQ and GPA. Well, if I went to graduate school and I looked at, okay, well, let's measure the IQ levels of our graduate students and then measure their GPA, that's probably a perfect example. To make it to graduate school, you usually have to be pretty hardworking and intelligent. So I'm like cherry picking the most intelligent people. So and everybody there is probably going to have a high GPA, so it's not going to look like a big relationship. But if I start taking into account maybe all college students, not just graduate school, but community college, university, everyone across, then I'm probably going to see this other area that I didn't see before. And then now we're talking about a strong positive relationship between the two variables. Whereas before, if I just had a select range, I wouldn't have that relationship. So you want to be careful to look at your data to see that that's not occurring. Another one is outliers. So outliers can definitely have an impact. So let's say we're taking some assessment and the majority of our people, they scored right here, but you have one person that scored way, way, way out here. Well, that's an unusual value. And if there's not anyone that is actually in this area, that's probably an outlier. Maybe they didn't understand the question, or maybe they just circled anything, they didn't care. But more than likely, that outlier should be removed, because if you keep that outlier, there's a relationship, and it says it's a strong relationship. But if you take out that outlier, this is basically not a relationship at all. So outliers are definitely going to have an effect on your results. So when you interpret correlation research, you want to also look at the scatter plots. So if you're actually doing research, you want to look at those scatter plots to see if there's outliers. So every one of our inferential tests has assumptions, and it's no different with the Pearson R correlation. So for Pearson R correlation, it has 3 very specific assumptions. Now, the most important ones really for Pearson R are normality and linearity. But homoscedasticity is also an important assumption, which just basically means that the variability across the regression line should be fairly equivalent. So if you'll notice, there's very little variance across the regression line in this area, okay? But then all of a sudden, at this area, there's this huge variance, huge variance. So that's a problem. So that would be problematic if we saw that in a scatter plot for Pearson R correlation. And the very most important is that we need to have linearity. We cannot run a Pearson R on data that's not linear. For example, this is what is considered a U-shaped data set. So in research, actually, this is an interesting one. In previous years, there was research done on marital satisfaction and the years married. And it actually, depending upon whether you're an optimist or a pessimist, researchers went into it with one of two hypotheses. They believed that either as the number of years in marriage increased, the marital satisfaction would increase, and they were thinking it was going to be on this line like this, okay? Or there's the pessimists that think, no, as years married go on, there's less satisfaction. People are more satisfied in the beginning, and they assumed there would be a line like this. Well, in actuality, in reality, they found that it looked like this, that U shape is what it did. Is in the very beginning, there was great satisfaction, but then the marital satisfaction dropped down, and they always usually call this the 7-year itch, but it's actually usually when people start having kids and that, they're no longer focused on the marriage, they're focusing on kids. But if people stick it out and don't get divorced and they really try to make things work, you can see the satisfaction going back up. Well, there is a relationship there, but it's not a Pearson R relationship. We can't use the Pearson R to look at data that is not linear. It's not on a straight line. So we would have to use a different type of correlation research analysis for that. And then normality is an important one. We can always assure that if we have 30 or more participants. So basically, with Pearson R, now you have normality in 3 different ways. You have normality for every X score, you have normality for every Y score, but you also have normality for the relationship between X and Y. So it's actually 4, but how they are correlated together, the X and Y's, there has to be normally distributed. So looking at X related to Y and Y related to X, basically. So those are some of the assumptions for us to be able to assure that our results are valid and appropriate results. So let's take a look at an example. So here would be an example of data that we would need to use a Pearson R for, and it's specifically to find a relationship between student hours of study per week and GPA. And so if you'll notice, it says N equals 7. That's because each of these belong to one person, and they're not, it's not like 2 separate conditions like with a related t-test. These are 2 separate variables measured for each person. So number of hours studied, if you study 40 hours, here's your GPA, 3.75, et cetera, et cetera. So each one of those study hours, the X scores, has a Y score. So if you notice, then there's 7, 1, 2, 3, 4, 5, 6, 7 X scores, and for those 7 X scores, there's 7 Y scores. But they're not treated as separate sample sizes because these are 2 different scores for each person that are related or we're looking for a relationship. So here's what we need to get started on our analysis. We need to state our hypotheses, the first step 1. So that basically by knowing what your actual hypothesis is, your alternative hypothesis, that is going to tell you whether it's a 1-tell test or a 2-tell test. So if I was to state that it's a non-directional, if it was 2-tell, I would just say GPA is significantly related to number of hours a student studies per week. Whereas if it was directional or 1-tell, I might say GPA has a positive relationship with number of hours a student studies per week. meaning then I would look at one tail and it would be a positive. It would be on the positive side. So knowing what the alternative hypothesis is very important for step 2, which is setting the criteria. So in this case, we're going to say this is a two-tailed test, that non-directional. So is what we need to do is find our degrees of freedom and look in our table for Pearson R correlation, which is table C5. So table C5, which in my textbook, it starts at 536, and I think it should be the same for yours, unless you're using an electronic textbook, it might differ. And remember, our sample size was 7, so we're gonna subtract 2 from it, because believe it or not, those are 2 independent means, because they're 2 different variables. So we are gonna do n minus 2. So our degrees of freedom is 5, and then we look in the 0.05 for 2-tail test, right? And we get 0.754. So our critical value should be positive and negative 0.754 for the Pearson R analysis related to GPA and study hours. Now we can actually start calculating the Pearson R, and here's the basic calculations. This is what you're going to need. So you're going to have to add up all your X scores. So you're just going to take the sum of those X's, and here's your sum of X right there. And then you're going to do just like before. You're going to square every individual X and add them up, and that's what's going on here. So we can get that sum of X squared. But then you're going to need to do the same thing for Y. You're going to add up your Y's and have your sum of Y there. And then you're going to square every Y. So here's the Y squared. So 3.75 squared, 3 squared, 3.25 squared. So now you have your sum of Y squared. But then you have the product of X and Y. So you have to multiply every X value to its corresponding Y value. So in this case, 40 times 3.75 is 150. 30 times 3 is 90. Etc. Once you get each of those products, then you can add those up and you have your sum of X, Y, which is 491.25. So those are just the basic calculations to set yourself up for calculating Pearson R. So those are what you're going to need to plug in. So if you'll notice, I put those calculations up here. So here's the basic calculations that we just went through, so that we can start working through what we need to get our Pearson R. So here's our ultimate equation right here, okay? So to get the sums of square of the product, this is what we need to do right here. Sums of square X, Y. So we take the sum of the product minus the sum of X times the sum of Y divided by N. So if you'll notice, the sum of X, Y right here goes right here, okay? Then we got the sum of X, so we just plug things in. This goes here, and then the sum of Y, this goes here, they get multiplied, and then sample size of N, sample size N is 7. So once you do those, you get 56.96, and that's your sums of squares X, Y, and you can plug it in right here. Then you need to get your sums of square X and your sums of square Y separately. So it's as simple as just doing your sums of squares as you have before, just plugging it in. So just replace the idea of X with Y. So then we have 1042.86 for our sums of square X, 3.18 for our sums of square Y, and we plug them in to the denominator. Now, one of the biggest things that I see students make, the biggest errors, is not putting the square root there. And then guess what happens? This number often comes out higher than 1. So be really careful that you're taking the square root of those numbers, because otherwise you have a real problem. You have to multiply those two together and then take the square root. And so go through And if you're writing your equations out, don't just plug things in and not have all of the notations you need. Because the plugging, if you plug information in and you're not really paying attention to the actual equation, it's easy to miss a step or to do it twice if you're not really careful. So now the next is if you notice, we got 0.99 for our obtained. Now we can get our effect size. The effect size for Pearson R is called the coefficient of determination. And this is complicated because R is known as the correlation coefficient, but the effect size is known as the coefficient of determination. And that's just basically the same as eta squared was, the proportion of variability in one variable that can be determined from the relationship with the other. So it's how much the relationship between the variables rely on one another, how much the probability is of those two variables relying on each other. And so it is literally R squared, and that is R obtained squared. So we take our 0.99 and we square it, and it ends up being 0.9801, meaning that 98% of the variability in GPA can be accounted for by the number of hours students studied. That's 98% of it. So that's very high, very high. So now we can state our decision in APA. So since how it was significant, because if you remember, 0.99 is larger than the critical value of I think it was 759 or 754. The criteria was 7.754. Sorry, that looked weird. So over here, we had negative 0.754. Over here, we had positive 0.754. Anywhere in the tails would be significant. Well, 0.99 is way over here. So that is significant. And it shows a positive. So it's a strong positive relationship. So you need to state that there's a significant positive relationship between GPA and our study. So both variables need to be described. Then you have your R, your degrees of freedom you use to look up your critical value, your obtained test statistic rounded to 2 decimals. And it should either, if it's negative, make sure you put the negative. If you don't have any sign, it's assumed positive. In this case, P was less than 0.05, and we used a 2-tell test. And then we report our effect size. R squared equals 0.98. It's that simple. It's a very simple test overall. So now that you've gone through Pearson R, we can actually talk about how we use Pearson R for what's called a regression. So Pearson R, it measures the linear relationship between the two variables. There's a line that goes through that data. And so that line helps us to see the relationship better. And it can kind of show us where the center of the relationship is. And we can use that line for prediction. So let's say I'm like really interested in, what is the, GPA related to IQ. Maybe I want to find out, okay, so what would the expected GPA be for someone who has just an average IQ, an IQ of 100? Well, if we have that regression equation, that regression using the correlation that we've done, if we use that, we can actually predict what the GPA would be for someone with an IQ of 100. So there's this potential for using regression to predict if we have a strong relationship between two variables. It's ineffective if we don't have a relationship at all. So there's some basic things with linear regression. We have to have two variables. We have to have what's called a predictor variable and a criterion variable. So the predictor variable is X, the criterion variable is Y. So basically, you can't swap those around. Just because maybe Y moves up as X moves up doesn't mean that if you decrease Y, Y will go down. It's only just, it's one predicts the other. So we're going to use that linear regression, basically with these pattern of data points. And if it's a significant relationship, we can start looking to see whether there's enough of a pattern to use it for prediction, what equation is best for that straight line that describes that pattern of data, and if the predictions are significant with the prediction equation. So that sounds very complex, but basically you're not going to want to even bother with a regression line to predict if there isn't a significant relationship between the two variables. So this probably looks familiar to you. You've probably done a regression equation or a regression line before in algebra. It just looks a little bit different in statistics for behavioral sciences. So the regression line or regression equation is also known as the best fitting line. So that line that goes through the center perfectly. And so you have your x variables, you have your y variables, and then you have your slope, and then you have a constant. So if you remember, y is the criterion variable or the outcome. So when we're talking about prediction, we're trying to predict an outcome, right? So you would be predicting y. So you would need the rest of this to predict y. So let's say our slope is 2 and our constant, which is a, is 17. If we try to predict what y would be using that information, let's say if we had the number 78, and so here's our data point, 78 right in here, we could plug 78 into that x right there, calculate this out, and find out what y would be. And if we had an x of 78, our y would be 173. And you can see that, it's over here. It's before 180. And so 78's here, and then 173's here. So that's how we can start predicting. And so even though there's not an actual data point that is exactly at 78 in the real data, it doesn't matter. If we plug in any number, if we have this regression line, if we want to plug in any number for x, we can solve for y and find out what that predicted y would be. So that's kind of the best feature for a regression equation. So now here's kind of to walk through that. So when I say what is the regression equation, it's the y equals bx plus a, is what you would need to do is solve for b and solve for a, is what you would need. So what we would do is find out our basic information. So here we have a set of 10 scores, and here's the sums of square x, the sums of squares y, the sums of squares product of x and y, and then we have our means of x and our means of y. So that's all we would need to get our slope and our constant to have a regression line. So basically, the first thing we want to do is find the slope. It's the sums of square xy divided by the sums of square x. Now, you can ignore this because in this case, you're not going to get this semester, but if you were doing a Pearson correlation on PSPP or SPSS, you wouldn't get the sums of square xy or the sums of square x, but it would give you your standard deviations and your R obtained. So you could always use the alternative method, which is R obtained times the standard deviation of y divided by the standard deviation of x. But in this class, you'll be dealing with the raw data. So you would have your sums of square of the product, which is 13.5 divided by 17, which is the sums of square x, and your slope is 0.79. Then you use that to get your constant. So it's the mean of y minus the slope times the mean of x. And once you get that, you get negative 1.45. Now, if you remember, the original equation is y equals bx plus a. So if you get a negative, that plus turns into a negative, right? So 0.79x minus 1.45. So basically, let's put it this way. If x is 0, if our x is 0, then our y is negative 1.45, right? So that's how you calculate this out, is you could plot several different data points and find what the scatter plot would look like for this in particular. So just as a kind of wrap up, when you're doing a Pearson R and you're testing a hypothesis, you're gonna stop right here. That's it. You're not gonna do a regression line equation. You're not gonna do all that. The only time you're gonna do a regression equation is if I ask you to specifically. If I say test the hypothesis using 0.05, this is what I'm looking for, is at the end, I want your APA result. The only time I would ask you for a regression line is for extra credit or on your homework or an activity. It's not something that I would have you do as part of the hypothesis test. It is a separate entity in itself completely. So don't worry about regression equation or the regression line for the test unless it's extra credit. So there are alternatives. So remember Pearson R, you have those assumptions, and one of them being the fact that it requires a linear relationship. But it's also necessary with a Pearson to have both variables measured on a continuous scale of measurement. But sometimes that's not always the case. Sometimes we have other measurement scales. So for Pearson R, what we just learned, both of the variables should be on an interval or ratio measurement scale. There are other types of correlation analyses that you can use if you have other types of variables. So you can use Spearman if both of your variables are ordinal. That's a good one, Spearman correlation coefficient. You would use the point biserial correlation coefficient if you have one variable that is nominal, but the other variable is interval or ratio. And you could use the phi correlation coefficient if both variables are nominal. So basically, the key with phi is the nominal data. So you're not going to learn these, but you need to know that there are other options, so that if you go into research methods and you happen to find out that maybe the research you're conducting fits one of these criteria more so than Pearson R, at least you know there's other options. So you don't always have to force your data to fit the analysis. There's other options for different types of analyses. And this could be an extra credit, you never know. So hopefully that helped clarify Pearson R correlation research and how regression is used. Regression is used much more extensively in future statistics courses, but for this class, that's all you need to know, is that it's used for prediction, and it is available as a method of prediction when you have a significant relationship between two variables. Please don't hesitate to ask questions and come see me during Cranium Cafe hours. Thanks.